the right horn spinners.
All right, I'll wait another minute or two, see who else shows up. Today at 6, we're going to have an alumni visitor to talk about his work with thin films.
So you have 2 choices. Okay. All right, Sarah, does that make sense at all? Okay, so you have a choice.
All right, I'll wait one more minute, see who else.
Okay.
My wife's just wrapping up her class right now.
Professor, can I ask you a quick question?
Sure.
I should have probably asked you this during office hours, but I know we're talking about photons and lights right now, but how come last class you didn't mention anything about Star Wars?
Why didn't I mention Star Wars in a discussion of photons?
Yeah, like lightsabers and stuff, and
Oh,
it was May 4th.
oh God. Okay, that's because this is a physics class and lightsabers are fiction.
But we're physics majors. I think it's kind of appropriate to bring that up during May 4th day, right?
Oh gosh. Oh God. No, I mean, I like Star Wars, but Christ, some people go way, 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 way too far with it. I mean, Lucas had the hero's journey. He had 2 good movies, and then there was one good spin-off movie, Rogue One. So there's been 3 decent. Actually, I like Jedi too. So I'd say there's been like 4 good Star Wars movies. Whatever. I've never. You know what Star Wars is like? Star Wars is like the Trojan War. If you look at Greek mythology and Greek drama, like everyone who got any mention in the Iliad winds up getting their own play. Okay, not literally everyone, but you know what I mean? There's like a whole bunch of Greek plays about all the different things that these characters from the Iliad did. Homer composes an amazingly good epic poem, and then every Greek dramatist feels the need, and some of them are quite good. Some of them, like this play Philoctetes, about a guy who had a magical bow and arrow that they would need to fight to win the Trojan War, and Odysseus has to go get it from him. And I mean, I'll be honest, if I think of it in terms of the Iliad, I don't give 1/10 of one crap about this magic bow. Okay, I mean, like every hero in Greek mythology was apparently at Troy. But the story of Philoctetes and his shame and his illness and everything, that was genuinely interesting. But like every single thing that gets mentioned anywhere in the Iliad gets mentioned in some other Greek play or some other mythological thing. I feel the same about Star Wars. There were like these 3 good movies, and then they made umpteen million spin-offs because people want even more of all of these characters. And whatever. I like to see a new franchise, a new story. I guess we're not going to get many more students today, which is a real shame considering we have an alumni visitor at 6. Is there a midterm or something for one of the other physics classes tomorrow that everyone's busy finishing up for? Won't be a midterm this week. Whatever. Okay. So last time we were talking about photons. And we talked a lot about the reason about the structure of molecules and their energy level diagrams. We talked about the fact that the typical process is that you absorb a high energy photon, and then there are some rapid vibrational losses, and then you emit a lower energy photon. Well, now what I want to talk about is the rates of these processes. All right, it's one thing to say, hey, a high energy photon can raise something from a low level to a high level. So what actually happens is that the rate of transitions is equal to a bunch of factors. First of all, it's got to depend on the intensity of the light hitting the molecule, all right? The more light coming in, the more likely it is to absorb a photon sooner rather than later and make an upward transition. So it's got to be proportional to the intensity. Now, if you think about it, every time there's an absorption event, there will be a transition. So every time a photon is absorbed, there'll be a transition. So we should really be thinking in terms of the number of photons coming in. So let's divide this intensity by h bar omega, the energy of one photon. Now we have photons per area times second instead of energy per area times second. All right, well, there's also this constant whose value I'm just going to kind of, whose source, whose derivation I'm just going to kind of punt on. This is called an absorption coefficient, all right, or an absorption cross section. And we can think of it as a cross section because for starters, if we look at the left side, we have units of 1/seconds. And after we have this, we've got units of 1/meters squared times seconds. So we have to multiply, whatever we multiply by has to have units of area. And so cross section as in cross-sectional area. Another way to think of it is you've got all these photons coming in. Well, what are the odds that they're actually going to hit the molecule and cause a transition? That's going to be proportional to something that's kind of like an area. Now we have to be a little bit careful because it's not always exactly equal to the effective area of the molecule. If you do the calculation, you will often find out that this is, in many cases, 10 to the minus 20 meters squared, which is 10 to the minus 10 meters, the square of 10 to the minus 10 meters. Now it makes sense because that's about the typical size of many of these molecules, or at least that's the size of one of the key portions of the orbital that the electron might be in. But it's not always equal to that. Sometimes it can actually be larger than that. Sometimes it's smaller, but it's a good rule of thumb. This is going to be the rate of upward transitions. That's where this absorption coefficient or this absorption cross section comes in. And you could ask, well, what determines the value of it? A whole bunch of complicated quantum mechanical calculations. Any questions so far? Well, then one question we could ask is, great, we've calculated the rate of upward transitions. What is the rate of light emission? What's the rate of fluorescence? And because it's one thing to get something up to the excited state, there is more than one way to lose energy and return to the ground state. I mean, you have to lose energy in order to return to the ground state. You don't have to lose that energy by emitting a photon. It's the most common way to do it, but there are other ways. You could transfer energy to a nearby molecule. You could lose the energy mechanically if the molecule is in, say, is suspended in a liquid and it's being constantly bombarded by collisions with other things around it. There are other ways. So that rate is going to be all the same stuff initially. You can't emit a photon unless you first go to an excited state. But then there's additional factor called K sub F, fluorescence efficiency. It's not always called K. There are other symbols for it, but this is a common one. And again, this depends on a whole bunch of details. To actually derive it from first principles, we would have to do some very elaborate calculations that include a realistic model for how this molecule might interact with its surroundings. That's a very specialized thing. What I want you to keep in mind is that these are things that people can measure through a variety of indirect methods. And so they can measure this and it is tabulated. You can look it up. It won't necessarily be measured for every scenario you want. If you say, all right, I've got rhodamine dye, that's a very common fluorescent dye molecule, and it's in this unusual solution, and this solution is in the interstices of a gel, and we've got this unusual pH. What is the fluorescence efficiency? Well, now we've just made the environment very Baroque, very elaborate. I don't know, there might be lots of ways to lose energy. But then again, some of those ways of losing energy might actually be rather unlikely when you look at how things interact. But these things are tabulated. These are the types of concepts or quantities you should be thinking in terms of, though, if you had to try to predict the rate of light emission from a molecule or from a suspension of molecules. This would be the rate of light emission by one molecule. Now, if I had a whole bunch of molecules, you might say, well, like if I had a beaker with a solution of whatever dye, all right? We've got our beaker, we've got our solution. We send in beam of light, goes in, it gets absorbed. There'd be a glow from there. Then, of course, the total rate of light emission, what I wrote here is from one molecule. Now the rate of light emission would be equal to, well, everything we got, it's going to be the one molecule rate multiplied by the number of molecules. The one molecule rate is the light intensity divided by the photon energy multiplied by an absorption coefficient multiplied by a fluorescence efficiency. multiplied by a concentration multiplied by a volume. Any questions so far? Well, as it stands, all I've done is just define a few things and say, if we want to calculate this, we have to look up a number. And so I've kind of punted the question. All I've really done is told you the name of the thing that you would have to Google for. But let's go a little bit farther with thinking about what happens here. Let's look at a two-level system. So a system where we don't have to worry about vibrational transitions. It's very simple. A photon can come in and excite absorption from our ground state, level 1, to our excited state, level 2. And then eventually it can return to the ground state and emit a photon. The rate of going from level 1 to level 2 would be equal to everything I just wrote down, I over h bar omega sigma, I'll drop the subscript, times n1. N1 is the number in level 1. So we're assuming that we have a collection of many atoms here. Now let's talk about the rate at which we can go from level 2 to level 1. Well, there's two ways. One is that a molecule that just happens to be in level 2 could emit. All right, it could emit light and go down to level 2. It just hangs out there for a while until eventually it does it spontaneously. That rate, first of all, has to be proportional to the number of atoms that are in level 2. And it's also got to be proportional to some constant. You know, for some molecules, this is a rapid, or some atoms, this is a rapid process. For some, it's a slow process. So we have to multiply by some constant. And I've chosen to, rather than multiplying by some letter that we put up in the numerator, divide by something in the denominator, because the constant we multiply by would have to have units of hertz, or 1 over seconds, right? Because it should be the rate at which this happens will be number of molecules per second. So we got to multiply by something with the units of 1 over seconds. I figured let's just divide by tau, which is a time. All right, it's just a fancy way of writing out the constant, and that constant is a property of the molecule. Any questions so far? It's not the only way that things can go from ground to, from excited to ground. Have I mentioned previously stimulated emission?
I think so.
Well, I'll review it. So stimulated emission is when you've got something that's in its excited state and a photon comes along that's at the exact frequency or very, very close to the frequency that it was going to emit. And then it falls and you've got 2 photons. And the basic way to think of this is that the atom is, it's like sound, you know, you have a tuning fork and it causes a string to vibrate at the frequency of the tuning fork if they're in tune. It's kind of like that. And it really is the atom vibrating, because in order for an atom to emit light, it's not so different from an antenna. Here's how an antenna works. An antenna is basically a big wire, and electrons go up and down in that wire. This oscillating current produces an oscillating field. Okay, well, on the microscopic level, an atom has an oscillating current. You've got electrons circulating. And the circular motion of the electrons is just another oscillating current. And that oscillating current can produce a light, can produce radiation, light. The big mystery to the pioneers of quantum mechanics was, well, why aren't atoms constantly emitting light? Because we've got these electrons in orbitals going around in circles. So if the electron is orbiting, isn't there already some oscillating charge here? If there's already oscillating charge, then why is it not just emitting light all the time? And then if it keeps on emitting light, it'll keep on losing energy. As it keeps on losing energy, it will fall lower and lower and lower and basically spiral in towards the nucleus. So in other words, why didn't all of the atoms in the universe just die in a massive outpouring of light right at the moment of the Big Bang? As soon as the atoms came into being, why didn't they immediately die? Actually, it wouldn't have been during the Big Bang. It would have been a few 100,000 years later, after the universe had cooled down enough that electrons could fall into stable, the electrons could fall into bound states around nuclei. But anyway, in the early universe, why didn't all of the atoms die? And it was basically the realization of quantum mechanics that things can't just spiral inward into lower and lower levels, because there's a bottom level. There's a level below which it can't fall. Anyway, so atoms are basically oscillating currents. Oscillating currents can emit light. It's not so different from vibrations of musical instruments. And so if there's energy to be given up here, then an incoming photon can stimulate emission. And one of the things that Einstein worked out was that this process should happen at the same rate as absorption. All right. That was one of the things that Einstein worked out in 1916. Or 1915. I think it was 1916. It's one of the most important things he did, because this is part of the theory of the laser. Without this, we wouldn't have lasers, so we wouldn't have fiber optic communications. So I wouldn't be able to talk to you remotely via Zoom. All right. The other thing that Einstein did was he worked out a relationship between tau and sigma, but we won't deal with that today. Okay. So fine, Einstein works out this relationship, lays down the theory of the laser. So we've got two processes by which we can go to the ground state. We've got spontaneous emission, and we've got stimulated emission. Now let's see here. The fraction of atoms in the ground state plus the fraction of atoms in the excited state has to add up to 1. And if we are in equilibrium, or at least in a steady state, the rate at which we go from 1 to 2 equals the rate at which we go from 2 to 1. Any questions about this? All right. So we're going to have that N1 times I sigma over H bar omega equals N2 times 1 over tau plus I sigma over H bar omega. And now what I'm going to do is I've got two equations and two unknowns. I could just do some basic algebra, and we will do some basic algebra, but I want to note something about units. I sigma over H bar omega, what are the units of that?
Wait, H bar and sigma, you said?
I sigma over H bar omega. Intensity times cross section divided by photon energy. Intensity is energy per area times time. Cross section is area. H bar omega is energy. Cancel, 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 cancel. Got 1 over time. I'm going to multiply both sides by tau. All right. And if I do that, N1 I sigma tau over H bar omega equals N2 times 1 plus I sigma tau over H bar omega. I've just gotten rid of units, okay? I'm now working in terms of dimensionless quantities. Dimensionless quantities are nice because if I say that a distance is, 2, well, do I mean 2 meters or 2 centimeters or 2 angstroms or 2 light years? But if I say that a distance is 2 times the wavelength, well, now I've just compared it to a physical yardstick, okay, to something with a very tangible physical meaning that would be independent of your units. You might measure wavelength in microns and someone else might measure it in nanometers, and aliens from another star system might measure it in some units that they call the Zuglacic, but it doesn't matter, okay? Because we would all know what hydrogen is, and we would all know that, okay, hydrogen going through this transition emits light with that wavelength. So if I said 2 times the wavelength of a given transition, we would know what that is. Or if I said that an energy is 3.7 times the energy of the photon emitted in a given transition, we would all know what that is. All right, so we often in more advanced realms of physics, as much as we yell at you about units in freshman and sophomore physics, in the more advanced realms of physics, we want to get away from units ASAP and work with dimensionless quantities, where you multiply a few things together so that the units wind up all canceling. I sigma tau over H bar omega. I could think of this as the number of photons per molecule per lifetime. Because if I over H bar omega equals photons per area per time, then I over H bar omega times sigma, well, that's just got to be the number hitting the cross section. All right, that's the number that would hit the cross-sectional area of one molecule. So that is photons per molecule per time. And if I then multiply by the lifetime, Instead of going for how many hit it in a second, I'm going with how many hit it in a lifetime. And so now it doesn't matter what units we measure the lifetime in. I measure the lifetime in nanoseconds, and you measure it in seconds, and someone else uses a completely different unit for God only knows what reason. But we can all talk about in terms of a physical process. So getting away from units is actually a way of going to more physical, picturesque language. Now this is photons per molecule per lifetime. And oftentimes when we do this, we give it a simpler name that might look like one of the symbols in there just with a prime on it. This is a very common notation. So what I've got now is that N1 I prime equals N2 times 1 plus I prime, and N1 plus N2 equals 1. All right, now we've got two equations, two unknowns. So I can say that N1 is equal to N2 times 1 over I prime plus I prime over I prime. I just took this top one and divided both sides by I prime, or N2 times 1 over I prime plus 1. Now I've got N2 plus N2 times 1 plus 1 over I prime equals 1. Or N2 times 2 plus 1 over I prime. So N2 is 1 over 2 plus 1 over I prime. Now let's just multiply top and bottom by I prime. Any questions on the process leading up to this before we get to the interpretation? No questions? Well, let's graph it. Or better yet, let's just take the limit as I prime goes to infinity of N2. Right? That limit is 1/2, which means if I crank up the laser power, I can't get more than half of the atoms into the excited state. So if this is 1, and this is 1/2, if I plot it versus intensity, it saturates at 1/2. Here's why that matters. A laser is an amplifier. Does anybody know what laser stands for? Light amplification by stimulated emission of radiation. That's what laser stands for. Light amplification by stimulated emission of radiation. We long ago stopped writing it as an acronym, but that's what it originally stood for. In order to get amplification, if you think about it, if I've got a whole bunch of atoms, I've got a collection of atoms. Some of them are in their excited state, and some of them are in their ground state. right? And then I send in a bunch of photons. Just a bunch of wiggles since light is a wave. Okay, well, what can these photons do? For any atom that's in its excited state, they can stimulate emission. For any atom that's in its ground state, the photon can get absorbed. Now, if most of the atoms are in their ground state, which process is more likely? Come on, think about it.
Absorption.
Absorption, yeah. But if most of them were in their excited state, then this would be more likely. Right? So the bad news is that a two-level system will not laze. Two-level system will not act as a laser. We won't get an amplifying effect. And we want an amplifying effect. The whole idea of the amplifying effect is that it purifies the light. You get a very, very pure light beam. And so all the calculations we've been doing, assuming a monochromatic wave, all of those hold. And it's only with monochromatic waves that you get the nice, clean interference effects that go in all of our calculations. So you want clean, pure light. And lasers give you clean, pure light. Clean, pure light can be focused more easily, collimated more easily. You can do more things with it. That's why lasers are so important. You get this nice, clean, pure light. And it's this runaway effect. What you've basically got in a laser is you have a cavity. You have something that the light is trapped in. It's often two curved mirrors. Sometimes it's two distributed Bragg reflectors. But whatever it is, you've got light bouncing back and forth in the system. And within that system, you've got a bunch of atoms or molecules or solids or whatever. You've got something in which electrons can absorb. You've got some substance that can absorb and emit light at the frequency that's bouncing back and forth. And you want it to bounce back and forth, and you want it to stay in there a long time and get amplified via some sort of runaway process, a chain reaction. Now, eventually the photons will escape because those cavities, those mirrors are never 100% reflective. They're 99.9 whatever percent reflective. And 99.9 whatever percent reflective means that each time it hits the mirror, there's only a small fraction of a percent chance of being transmitted, which means that there's a very good chance of bouncing back and forth. You might have to bounce back and forth thousands or tens of thousands of times before it escapes. That's a whole lot of time for the light to bounce back and forth and get purified. Here's a good analogy for it. You know what happens when someone gets in front of a microphone and then you hear a feedback whine? You know, and all of a sudden, as you hear that feedback whine, a person tries to speak, and you just hear this pure note. It's loud, it's often high-pitched, but it's very, very pure. That is actually, that's an acoustic version of lasing, because what's happening is that we've got an amplifier, it's the microphone and speakers. Sound enters the microphone, and it gets amplified. Now, an ideal microphone and speaker would produce a signal that has the exact same frequency spectrum, the exact same range of frequencies and relative proportion of frequencies as the speech that went in, okay? But in practice, it never amplifies perfectly evenly. There's some frequency that gets a little more amplified relative to all the others. Now, all the sound that comes out of the speaker goes into the room, and some of it will make it back to the microphone. That's the feedback. That's why they call it feedback, because you speak, goes out of a microphone. That's why when I log on to Zoom and then I connect a second device, you often hear it go, like the shower scene in the movie Psycho. All right, that music, which was very high pitched and repetitive. It's the same idea. So the sound comes back and it's not exact. It comes back to the microphone. There's some frequency that made its way to the microphone a little bit better than the others. So that whatever goes back into the microphone, one frequency will be a little bit louder than it was initially. Goes in, comes back out. Same thing happens. That one frequency gets amplified a little more. Goes back in, gets amplified even a little more. Maybe the others are getting amplified too, but not nearly as much. Okay, one of them is building up way more than the others. That is actually a perfect analog. Perfect is a strong word. It's an amazingly good analog of a laser. Any questions? All right, so lasers, they exist. We know that they work, but we can't make them happen with two-level systems. So what is the obvious conclusion? A system with only two energy levels cannot be a good basis for a laser. So given that that statement is true, we proved it here. It saturates at 1/2. There will always be more atoms in the ground state than the excited state, which means that in a two-level system, you'll never achieve what they call population inversion. Just mean that we reverse things so that we get more in the excited than the ground. Can't happen in two-level systems, but lasers exist. So what do you think people do?
One level system? I don't know.
Well, if there's a one-level system, there's no transitions at all.
Oh, so then we increase it then.
Yep, 3 and 4 level systems. I'm not going to write down all of the equations because it's just a slightly more complicated version of what we already did. Some algebraic gymnastics, but here's the idea. This would be the simplest 3-level laser. All right, we send in light like this. We have a pump beam. And then there's a rapid transition. From level 3 to level 2. That would be very, very rapid. Okay. And then it waits for a long time up here. The 2-to-1 transition is slow, okay? But eventually it will happen. And I should have indicated this in blue because it's higher energy, shorter wavelength. But then eventually we can get a downward transition. So we can get way more atoms into level 2 than level 1, because if we crank up the pump intensity, all right, we can blast atoms out of level 2 And you might say, well, won't we be stimulating some 3-1 transitions? Won't that pump beam also stimulate some transitions from level 3 to level 1? Yeah, it certainly will stimulate some transitions, but there's hardly any atoms in level 3. As soon as they get to level 3, they just rapidly decay to level 2. They decay very rapidly so that it's going to take a long time for stimulated emission to do anything, to pull anything out of level 3. Okay, you'd have to have a really, really, really intense beam in order to send things from 3 to 1 more rapidly than this 3 to 2 transition. But everything is just chilling and relaxing in level 2, right? Then eventually one of the atoms emits. It sends out a photon. Over here, we have another atom that was in level 2, just hanging out, and it sees this photon come in, and it decides to emit. You might say, well, couldn't it also raise something up from 1 to 2 in principle? But, you know, you would have to compete with the pump process. Any questions on the idea of how that could give you population inversion? Often what people do is they work with a 4-level system, even better. 1, 2, 3, 4, right? The pump beam does this. This process going from 4 to 3 is fast. It will eventually go from 3 to 2. This is slow. And once it gets to 2, this is fast. So there are very few, the pump beam is going to have a hard time sending anything from 4 to 1 because, you know, as soon as it gets to 4, it almost immediately goes to 3. And this photon that got emitted, it's going to have a hard time finding another atom that's in level 2. If it did find an atom that was in level 2, then, you know, it could always raise something from 2 to 3. But in order to do that, it would have to find one. And this process here is fast. So mostly what happens, by far the most likely thing to happen, is that this photon will come along and find something chilling in level 3 and send it down to level 2. And then there will be 2 photons. And then these 2 photons, each of them comes along and finds a couple more systems that were up in level 3. And now we have a chain reaction. Any questions? This is obviously far from a complete description of how lasers work, but since we were talking about what a photon is and we're talking about an absorption cross-section, I wanted to give you a context in which absorption cross-section matters besides the fluorescence stuff. I'm going to return to fluorescence microscopy next Tuesday and talk about some interesting things that people can do with fluorescence microscopy to get around problems involving 3-dimensional imaging and even get around problems like the diffraction limit and show you some of the cleverest things that people have done in science in a few decades. And then next Thursday, we will just go over your final project assignment, which will be revealed next Thursday. Any questions on this?
I actually had one question, Professor.
Sure.
I just want to understand what the pump is. What physically do we do to actually create that pump to push it up?
Often it's electrical pumping. We apply a voltage to raise electrons to a higher energy level. Sometimes it's an optical pump. They send in light. They basically have one laser pump another laser, or they have a flash lamp pump a laser. So you send in light. That's common in dye lasers. You send in light, and the light raises things from the ground state to an excited state. That's the pump that gets everything into a higher energy level to get the lasing going. So you can either do it with a voltage or with another light source. In the end, both of them are electromagnetic fields. The key difference is that the voltage is usually DC, or at least very low frequency AC, whereas the optical pumping is very high frequency. All right, at 6 o'clock, an alum is going to be coming. There's low attendance today, but you might want to mention on whatever Discord you guys use to discuss assignments and stuff for this class, that at 6 o'clock, someone who works in the optics industry is coming to talk about what they do with thin films. Maybe a few more people will log in. We're going to take a short break, and then I'll come back at 6. right, Kyle, I see you're here. Good to see you. Can you hear
It's
me?
good to hear you.
Hopefully we'll be able to meet in person at an Optical Society meeting soon.
Yeah, that would be cool.
Apparently we're going back to in-person meetings this October.
Well, that's great.
Program year resumes. All right, you have a presentation. You want to test the screen sharing?
Yeah. How's that?
Good. Let's just wait another minute or two. We were on a 10-minute break after the first half of class. And so everybody will be back in about 1 minute.
Is this the full class? It's a little smaller than when I took it with you.
Well, online classes haven't had quite the same retention rate that in-person classes have. So yeah, it is a little bit sparse today. I can't wait to go back to in-person. Anyway, it is 6 o'clock, so let's get started. We're going to be hearing from Kyle Haddock, who graduated from Cal Poly with a physics degree in 2018. He took this class, he did his senior project on thin films, and he is now an application engineer at Optosigma down in Orange County. And I'll let Kyle take it from here.
All right, thanks for the introduction, Dr. Small. Hi guys, I'm Kyle Haddock. I'm graduated from Cal Poly in 2018, just like Dr. Small said. During my time there, I was a physics learning assistant, which was a really great experience. If you guys are really inclined and have the time, I highly recommend doing it. You get a little bit of money out of it, and it's just a good experience. I think obviously it's gonna be more realistic when we're back in class because it's kind of a in-class type of thing. But you know, I still encourage it, still put it forward. So yeah, while I was here, at Cal Poly, I focused on optics and Python programming, and kind of merged the two and worked on probably the thin film program you guys worked on. Probably are familiar with, I would think as well.
Yeah, they're using it.
Okay. Let's see if I can get my video on. Oh, there we go. Hey. So yeah, I started. Dr. Small is one of the. I think he's the one who actually saw the job offering from Optosigma, and so I interviewed with them, and they really liked me, and it seemed like a good fit, and it was pretty close by, and I'm from Southern California, so I wanted to be by my family. So that's how I ended up there. The internship turned into a job. It was really just a stroke of luck. And yeah, so I've been there for almost 3 years now, and it's a great job. I love it. So a little bit about Optosigma. It's been around since 1995. They've been located in Santa Ana. They originally were in Irvine, and then they moved. So we have manufacturing done in Japan and China. The company Optosigma, it's like a brand, a global brand of like a Japanese company called Sigma Koki. Sigma Koki's been around for almost 50 years, producing precision optics and other optical components. They're really popular in Asia, and so that's their main market. And so we're kind of the global brand for distribution in North America. Separate from them, though, we do have our own optical coating lab, which we take full advantage of, and we do optical coatings all day, every day, Monday through Friday. And so, yeah, we have a huge catalog, but a lot of what we do is also custom as well. So I'm just going to blow through some of our main things that we have. So yeah, this is kind of like some stuff from our catalog. We do a lot of optical, high reflective mirrors and stuff like that, ultra broadband mirrors. Some of these ones that are clear looking are probably highly reflective for near infrared light. We also have a huge selection of catalog optics, and we also do, but like I said, most of what we do is actually custom. So kind of we have a healthy balance of both catalog and custom. It's kind of beam splitters is, useful with lasers if you need to, separate your beam in two different paths, or separate by polarization state. Filters out a certain kind of light, certain wavelengths, certain intensity. So keep going with the optics. We got polarizers, objectives, optical assemblies. So we do a lot of custom work for these optical assemblies too. A lot of our custom optical assemblies end up in, interferometry devices. So it's pretty interesting. Basically, when you have all these nice precision mirrors and lenses and stuff, you have to have a way to hold it. So that's literally what optomechanics is. It's just the holders and positioning stuff. Then we have manual positioners, similar to optomechanics, except these can be used for a variety of applications. I had no idea about these kind of devices until I actually got to OptoSigma, but they're extremely important and super useful in many different applications, both optic related and non-optic related. A lot of times when you're working with a laser or some sort of optical system, the sensitivity of your beam path is, you're working in the light is in nanometers. And so you have to be precise down to microns. And so a lot of these can move with like what you can actually make a precise movement of 10 microns or less sometimes. Motorized positioners, same thing. I had no idea about these things, but again, very important in array of applications, including optics and non-optics related as well. Some of these can go down to like about 100 or 200 nanometers precise movement. So being an application engineer, it's kind of like a jack of all trades position, essentially. I wear a lot of different hats. I do customer service and like in terms of like technical support or helping a customer find the right product for them, or even talking with them about a custom product when our catalog one doesn't meet their needs. So that's a lot of what I do. A lot of emailing, having Zoom calls now. But if people are local, sometimes I'll go out with a sales manager and we'll go do a sales meeting or something like that. And I'm kind of like the technical person to talk about the company. So it's pretty interesting. Being an application engineer, you kind of have to know at least a little bit about almost all the products in a catalog, and our catalog has over 15,000 items. So I'm always learning new things about our stuff every day. One of the coolest things that I do is designing optical coatings. And again, my interest in optical coatings really started in this class that you guys are taking right now. And so I was really interested in how these kind of, you guys did the Bragg reflectors with the quarter wave stacks. So I was interested to know like how what more you could do with it. And it kind of just led me down this rabbit hole that I'm still in right now. And so yeah, my kind of my research at Cal Poly Pomona is what kind of made Optosigma, they were really interested in that because they didn't have anyone to do any coding design at the time when I first started. So right when I first started, it was a lot of learning because you go from a purely theoretical to actually working with this stuff and seeing the chambers and everything like that's totally different. So now I work with the coding manager that we've hired, and he is just a vast source of knowledge and help. And so I've really grown with him, and he's really showed me how to do the things I want to do with my designs and everything like that. Another cool thing that I've got to learn through my time at Optosigma is 3D Cad modeling. So like designing 3D parts, or modeling some of our manual and motorized positioners together. I recently designed a system using all of our catalog components that holds these stages and they're positioned over like a tank, and they're going to do hydrophonic water, basically sound and water type stuff. So I thought that was really cool. It's really fun to work on. And then more recently, I've been trying to get as best as I can with Zmax. I think, have you guys been doing any Zmax this semester?
Lots of Zmax.
Yeah, great. So that's such a useful skill if you guys are going to end up in optics or any sort of like optics related job or field. Just a lot. This is Zmax. There's other programs out there, but Zmax is an industry standard. Sometimes people, they just send their Zmax file and they say, hey, this is what I need. It's, please quote from my Zmax file. And, just being able to read that is, already important, because if I didn't have like this kind of background knowledge, I wouldn't be able to at least build upon that. So I've been taking some classes at the UCI Department of Continuing Education, Optical Engineering certificate program. I highly recommend that. If you guys are really interested in optics, it'll give you kind of additional education in Zmax. You do a little bit of 3D modeling as well. But yeah, it's just a really good program, and highly recommend it.
Did you find that there were any gaps in what you needed to know, like in prereq knowledge to start that class at UCI?
Oh, no, absolutely not. I feel like anyone who's taken this class or Dr. Salik's optics class, I feel like even if you didn't necessarily take those classes, they're geared towards people who are not necessarily coming from this field. So it's pretty good. I would say that I wouldn't feel I would say I wouldn't think I hope people wouldn't feel intimidated to take it, because I don't think they're like super like you have to have like some sort of base knowledge. It's just more of like, I feel like they're really good about teaching what you need to in the class. But I think at least like when you take every class there's like a list of like kind of prerequisites, or it's kind of like what they hope you already know. And when I look at it, most of the time it's like pre-calculus and stuff like that. So it's stuff that you guys would already be at that level anyway.
Okay.
So yeah, kind of going into optical coatings here. Like I said, I was first introduced to optical coatings in Dr. Small's applied optics class you guys are taking now. My research project was focused on simulating optical coatings and filters using Python. And so after I started working at Optosigma, they were really interested for me to continue doing optical coating design, and they use a specific program because a lot of times companies, or when you're doing optical coating design, you want to use a good program that works well with your process, I guess. So they sent me to take this class with Angus MacLeod. He actually recently passed away. And yeah, he was amazing. I cannot say enough good things about him. I reached out to him even as recently as like Matt last year asking a question about the software, and he was always, you know, answering my question, or his daughter was. And so, yeah, that was a really good class. And I also got to train, I also got to go to Japan. Like I said, the majority of our manufacturing is based out of Japan. I actually got to go for 1 month, and I got to go to our optics factory for the majority of that time, at least for 2 weeks. And then I got to go to our technology factory, and then our basically kind of like our, I don't know how to call it, like our metal working shop where all of our metal components are made, our stages and everything like that. Huge factories. So yeah, it was really good. I learned so much about, because really you see these lenses in like an objective or whatever, but you have like no idea how it's really made. So it was really interesting and really good experience to go do that. So yeah, at OptoSigma, the majority of the coatings I do are AR coatings. Basically, like when you have lenses and we're selling a lot of them, you know, to one customer, it kind of, the AR coating is, it's not only adds value, but it also increases the performance of the lens. So you're really just getting more out of it. We also do HRs, fancy word for like a dielectric mirror. So high reflector, partial reflectors, kind of like a filter coating, beam splitter, exactly what it sounds like. And dichroics, dichroic mirror just basically means it allows certain wavelengths to pass and certain wavelengths to be reflected. And also what we do as well is we kind of specialize in this high damage threshold, meaning that a lot of our AR and HR coatings and filter coatings end up in medical lasers that are used for laser hair removal or tattoo removal as well. So yeah, this is kind of a snapshot of our coating lab. We do the HR coatings in this white one. It's slightly bigger and has a plasma ionosis, and I'll get to that in a minute. These two on the side, they're the twins. They're old, but they've been stripped and retrofitted with a bunch of new gadgets inside. So yeah, we do a lot of ARs in these ones. So I'm just gonna have you guys talked about like, because I had no idea. It's one thing to like just talk about the coatings, but like I had zero idea about any of this stuff before I actually got to OptoSigma. So
We haven't said much about the materials processing.
okay. So yeah, I kind of just hit on like a base level, and I'll get into some specific kinds or whatever. So I in my presentation, I have 2 types, but there's way more than 2 types. I'm going through the most basic kinds, the most common out there. So the first type is called electron beam deposition. Like I said, it's one of the most popular kinds, common kinds. And the way that it works is that you have a powerful electromagnet. And what the electromagnet does is it takes, it basically accelerates and channels electrons from an electron source, which is usually like a tungsten filament. And those electrons bombard the evaporation material in the crucible here. And these materials are typically oxides. So some of the most popular is like silicon dioxide, aluminum oxide, tantalum oxide, titanium oxide. But it could also be fluorides and other materials as well. So basically the electrons hit your coating material. And what happens is it sublimates, it just changes instantly from a solid to a gas state. And it's basically evaporated. And the evaporated coating material is ejected upwards and lands onto our lenses that are spinning above here. And we want to spin our lenses because it ensures that we get an even coating all around the lens or the substrate. So that's the first type. There's other components in here. It's important to have, or one of the things I guess I neglected to say is like, with these type of chambers, it has these incredibly powerful vacuum pumps. And what happens is before any of this starts is we pump out all of the air as much as we can, and we get down to a base level of something like 10, probably like 5 times 10 to the -5 torr. So really low vacuum levels. And we do that because if we didn't do that, the coating materials would interact with the air in the chamber, and it would basically cause
Uh-oh. Internet issues. Can you guys hear me?
Oh
I
yeah,
think
I
it's
thought
just
that
us.
was me.
No, it's Kyle's connection.
hopefully that's better.
Yeah, we can hear you now. The last thing we heard was something about why you're pumping down. You're saying it would interact with the air molecules and then
Yeah.
lost it.
Okay. Thank you. So yeah, there's a number of reasons why you want to pump out the air. You don't want your coating material to interact with the air molecules or basically slow them down from getting here. You wouldn't have as high of a packing density, which the packing density or the density of the film is directly related to the refractive index that you end up with. And then the other reason is you can trap water and air molecules within the film. And that's another reason why your index would come out very strange, and your film would not be a very good one.
It would probably also cause mechanical problems over time, right? There'd be some sort of, I would imagine that the oxygen in the air and the water, those are both highly reactive. So that might cause some deterioration.
Yeah, exactly. It's just, it totally affects the durability as well. Yeah, so that's basically how electron beam deposition works. So we spin. So the second type is very similar. It's called ion beam sputtering. So it's very similar to E-beam, except that it uses an ion source instead of an electron beam. So it uses charged argon particles, and they're ejected from the ion source. They hit this target right here, and the target has your coating material on it. And then the coating material becomes ejected and hits your substrates up here. Again, we're spinning at the same time. We want to ensure an even coating, and we're also pumped down as well to a really low base level. These are becoming more and more popular because of the growth of ultra fast optics, meaning lasers that have femtosecond pulses. And so this is kind of like a better technology for that type of laser and stuff like that. So a lot of times, so these are kind of like the two basic types. And so a lot of times these kind of chambers, they'll have extra features on them. A lot of basically what you'll see nowadays is it's called IAD or plasma IAD, ion assisted deposition or plasma ion assisted deposition. And so basically, if you could look at this diagram on the left, this kind of represents the coating material being ejected and landing on the substrates while the substrates are spinning. And similarly, how the ion gun works to eject the coating material, it's a less powerful version of that. And what it does is it sends charged particles at the surface, and it bombards them. And what it does is it helps ensure a better packing density, which will ensure a better refractive index that's closer to the bulk material. And when we say bulk material, we're talking about like the real, like not a film, an actual piece of that crystal or whatever it is, that material. So yeah, E-beam, it's not required to have IAD, but it's typically a lot better in terms of mechanical stress, durability, and refractive index. The second one I want to get into is related to ion beam sputtering. It's called magnetron sputtering. And it's very similar. It's exactly the same as IBS. But there's a magnetron that's used to accelerate ions towards the coating materials, causing the coating material to be ejected on the substrates below. It's a powerful new technology. It's not new per se, but they've just really perfected it in recent years. It allows you to get the most dense films possible, and one of the downfalls with IBS is that IBS is typically much slower compared to E-beam evaporation. But with the magnetron, it basically really speeds that up. So you get the best of both worlds because you get the high dense films and you also get the fast deposition time. So kind of the best of both worlds. The last thing that I want to get to is called optical monitoring. So if we look back at these other ones, you can see here there's a crystal type film thickness meter, thickness monitor. So basically you have to know when you should stop coating that material, right? Because you only have a few nanometers of material where your coating might not be working the same anymore. So you have to know precisely when to stop your coating so you don't coat too much or don't coat too little. And so there's two different types. The first one's called crystal monitoring. It's basically uses some type of crystal, and then it basically detects the change in frequency of the crystal based on how much material has been coated onto it. It's definitely a reliable way, but it only measures your thickness of your coating. It doesn't measure your refractive index, which is super important as well. So one of these, the new type is called optical monitoring, and it's a step better than crystal monitoring because it uses a broadband light source. So it can measure your refractive index over a wide range of wavelengths, but it also detects your thickness as well. And so this basically is a game changer because this will allow you to make a design, and then because this is a in-process monitoring, it almost ensures with such a high probability that your design will come out as exactly as you intended. So it's a really, all of our chambers in Japan, like almost all of them have this technology, and it's really amazing. So I just wanted to throw out some interesting applications for optical coatings. I threw out the Perseverance rover, Opto-Sigma and Sigma Koki made over half the optics that went into the SuperCam. I think it's this big actually head right here. So our optics are on another planet. So that's really cool. We're really excited about that. And like I said before, a lot of our coatings and stuff end up in laser tattoo removals and also laser eye surgery machines, and also laser machining. We sell a lot of lenses that get used in welding and all different kinds of laser machining applications, laser marking, all different kinds of stuff. So yeah, I think that's it.
All right. People must have questions for Kyle. Ask away, and turn on your camera if you don't mind when you ask your question.
I have
I'll
a
start.
question.
Oh, go ahead.
If you don't mind, sorry.
Yeah, go ahead.
Yeah, so when you did your first internship, what were some of the things that you did in that internship? at your
Great
company?
question. Basically, I cleaned out like this kind of work area, and it was basically told to me like, hey, like, when you start working here, we want you to do some, kind of checking out some of our products and working with like a coworker who does some assembly stuff. So I helped clean out that, get it really nice and organized so that, because they said, you're going to work here, so you should make it look nice how you want it. So what else did I do? I kind of played around with a lot of the products. I got really familiar with a lot of their products there. Kind kind of was involved in like a few meetings about, talking about certain problems that were going on with customers and just trying to be as helpful as I could. The internship honestly was only for maybe 2 to 3 months, and I was only going about 2 times a week. So it wasn't as involved as you might do in like a summer internship. But yeah, I worked a little bit with the coding team and stuff like that, just, kind of learning about the process and stuff like that.
Is
Because
it
like
okay
I,
to ask? Oh,
no, go for it.
I was just gonna ask a follow-up question.
Yeah.
I actually live in Santa Ana, and I've never heard of your company. But
Mhm.
how often do you do internship opportunities at your company, especially with COVID as of recent?
I mean, honestly, I did hear that they wanted to get more interns for this summer. We didn't have any last summer, but we had some the summer before. One was a mechanical engineer from Cal Poly. The other two were from the Midwest. I think one of them went to Purdue and another one went to University of Illinois Urbana-Champaign. So yeah, I mean, 2 of them were engineering and one of them was marketing. So, but yeah, the last thing I heard was that we were trying to have interns. So, yeah, if you want to send me an email, my email's right here, just my name at OptoSigma. You can just do Kyle at OptoSigma too. And yeah, so send me an email and I'll talk with my boss and if that's actually going to happen or not this year.
Okay, thank you so much.
Yep.
Other questions?
That's for everyone too. So just if people already don't have their summer planned out, or if you're interested in doing astronomy or something, but if you're interested in optics, just reach out to me and I'll see if we're gonna have interns this summer.
Kenneth, it looks like you want to ask a question.
Hello, Kyle. So yeah, I have 2 questions, I guess. So what kind of skills or software should we focus if we want to land, I guess, like an internship at OptoSigma, or if we want to work there?
It's a good question. Again, like when I started it, I knew what you guys knew. I did some ZMAX. I had an interest in optical coatings, and I had a physics degree, and so I don't think anything is necessarily required. I mean, this is generally speaking as well. I think a lot of places it's good if you have some sort of experience or something, an area that you're really interested in, because that kind of makes you stand out from maybe a candidate who's just kind of more general, who, they don't have a specific interest in something. But yeah, I think a lot of places will understand or, realize that you're coming right out of college and you're going to have so many skills. And I think really what's going to help you is any sort of experience you can get, research experience, internship experience, and those are going to be really good. So I don't think it always, if you can do software, it's good, but it's not going to be. I wouldn't think it's going to be make or break at the, right after you graduate.
Okay, so I think like as for like other students, including me, we're currently taking applied optics, and we're gonna take Professor Salik's wave optics soon. And I know a good amount of students are also taking computational physics too.
Yeah.
So I've heard that's like a strong like combo, I guess, for I guess internships and stuff. But I was gonna ask you, since like as undergrads, we don't have a lot of industry experience, and what would you recommend us doing to land an internship? But I guess you said like senior project or senior research is a good idea. But is there anything else? Maybe like independent like research, like I don't know, like during the summer, or like I don't know.
Yeah, no, that's a good question. Definitely, if you're going to take, this is for everyone. If you're going to take Dr. Sleek's class in the fall, if he still does the class the same way, and I'm hoping, hopefully everything's going to be in class and you guys get to get in the lab and have that lab. But really just focus on those 2 labs. I think if he still teaches the same way, he gives you 2 labs. Maybe it's 3 now since you do semesters instead of quarters. But really just hammer them, like give it 150%. Make sure you're doing everything the right way, and because that's kind of, even if you don't get that other research experience or that in-person experience, at least you can say you did this project and you really understand what you did in that project. And if you can explain that to somebody, then that, I don't know, that's basically just validates that you knew exactly what you were doing and you know your stuff. So yeah, even if you can't necessarily get those, because for me, I totally messed up on, I was a transfer student and I really wasn't aware that there was research programs you could apply for and all these type of things. I had no idea until it was too late. So I thought I was totally sunk, but at least I did pretty well in Dr. Sleek's class, and I, did my research project, and I feel like those kind of redeemed me, I guess. So.
Could you say
Yeah.
a little more about your senior project, what you did in it?
Yeah, so for my senior project, I used the Python code that you guys have worked with. I kind of added additional materials to it. So I was working with a variety of materials. Some of them were like niobium pentaoxide and tantalum, TiO2, because what I did with my research project is I found patents on Google Scholar, and I pulled up these patents for these filters. And so I basically simulated these filters, and I tried to see how accurate it was from the program versus the actual result. And so
it's hard to know whether the result claimed in the patent is fully representative, because the art of writing a patent is to disclose as little as possible while meeting the requirements of the law.
Right. Yeah. So yeah, it was really just kind of using the program and seeing what these filters would look like, and how accurate they were, I guess, with the program itself.
Other questions? So how much of your time is spent working with customers versus designing processes in the thin film facility?
It just kind of depends. I feel like a lot of times we'll get a request, or somebody's interested in something, a coating, and I'll just kind of, in a way to kind of attract them, I design a nice coating, and I'll send them kind of like a picture of the result. And so that's kind of, and so it doesn't take me super long to make like a nice AR. Kind of got the process down at this point. So I kind of like give them a little taste of what they could expect. And so that's kind of a lot of what I do. And then when it actually becomes an order, then I go to the lab and we run a test run, and we just verify, the test run verifies that it comes out, my design and the result is matching. So I'd say probably about a third, maybe 25% to a third. But I'm also recently getting into troubleshooting optical assemblies and working on optical assemblies. So right now I'm going to work on a custom beam expander that we make for a customer. They're having a problem with one of the elements. It's causing the beam to like shoot off at a strange angle. So it's kind of a misalignment of the two lenses, and I'm kind of gonna diagnose that. And another one I'm working on too is this cavity. It's like a cavity type thing called cavity ring down spectroscopy. It's really interesting. Uses super highly reflective mirrors to create a really long path link, and it can detect certain amounts of really small amounts of material in the atmosphere. So kind of working on that too. That's been a little bit, maybe like 20 or 30% as well. And then probably the rest of the time is talking with customers about custom items, or I'm also involved in just being an engineer. You have to do a lot of checking documents and kind of doing your homework on when we get new orders, making sure we have everything that we need. So that's another part of it too.
Ben, did you want to ask a question? Can't hear you.
There we go. So I was wondering, when you first started, how much supervision did you have versus maybe now? Like,
Oh, I talk to my boss all the time. Yeah, honestly, like my boss is a physics major, so you know, like we both understand, like we're on the same level in terms of that. So like I said, he was super. I made it. I'm not going to say I highlighted my faults or something, but I made it abundantly clear like what I knew and what I didn't know and what I was interested to learn. And so my boss has always been there to, you know, help explain something I don't understand or something like that. So yeah, I'd say, I guess it's about the same amount. It's always been kind of, I guess I haven't necessarily needed a lot of supervision in terms of I've always worked in like customer service positions. So I've I worked in like Jamba Juice and Panera Bread and all these places. And so I can speak with customers and stuff like that, no problem. So it's just more of like in terms of how an actual business like this runs. Yeah, I had no idea about that. So yeah, I don't know. I guess about the same. I feel like I don't feel like I'm being managed. Like, and when I do, it's from the sales manager. It's not from my engineering manager.
I want to ask a follow-up on that. Since you mentioned, you know, working in the sorts of jobs that people get before they get jobs in their major, what's the best way to pitch that on a resume or in an interview? You know, some people I think are going to be very self-conscious about, oh, I've only worked at Jamba Juice or whatever. But you know, you clearly pointed out that you were comfortable with customers. So what would you recommend saying about those kinds of jobs if you're in an interview?
So basically, what we're saying is like, what qualities or what things you did well in that position translate to this new job. And you know, specifically for me, like, I don't know, I always was ended up at these places for a little while, like a year or so, and I had a knack for being a shift supervisor. So maybe that's why it's like I always got promoted to be a manager at these places. So that was one thing for me, at least. But I mean, if you work at a place for 2 or 3 years, it shows that you're dedicated, you know. So at least even if you're working with, you know, Jamba Juice or smoothies or Starbucks or something like that, you have personal skills. You know how to work with other people. You can be in an office and work with other people, and they're not going to be, you know, worried about that or something. But I have to say, I feel like it just depends on what type of thing you do. Like when I worked at Panera Bread or Jamba Juice, like these places were crazy busy. So like my multitasking skills was, you know, I had to be really good multitasker. Otherwise I couldn't get my things done in the amount of time I had to do it.
So I guess the big takeaway is to just look for how it shows that you're a good worker and not be self-conscious. Because I talk to a lot of students who say, oh, you know, I've only worked as a cashier before, or I've only worked as a whatever. And, you know, they're kind of, and I'm not trying to put it down, but they're self-conscious about the fact that it doesn't seem on the surface like it directly relates. And you're saying, you know, it's a job, you did it well, focus on that.
Yeah, exactly. Like own it. Don't be ashamed of it, because especially if you know, I mean, I didn't put like, when I came to Cal Poly, I quit all those jobs because I had saved up enough money and I got accepted and I just wanted to focus on physics. So I didn't like put something, but if you have a great relationship with a manager, like from your first job or something like that, that's, you know, that just shows that you know, you did a good job and they're willing to put their, to say good things about you. But yeah, no, don't feel self-conscious because like I said, unless you get that internship experience or that, you know, research experience, then that's the kind of professional experience that you have. And there's nothing wrong with that. I know it shows that you've worked before, you know, you have work ethic. So you're capable of holding a job. That says a lot right there. Just like when you graduate with your degree, it says you can follow through, finish your degree. It's just, these things say more than just, oh, I worked at this place. It says there's other things that come with it too. And you should be using them to your advantage.
All right, Felipe, it looks like you have a follow-up. I just want to see if there's anyone who hasn't asked a question yet that would like to chime in, Madison or Maximum or Jerry or Leona or Andrew. All right, not hearing anything. Felipe, go ahead, and then there'll be time for other people to ask questions.
Oh, hi, Kyle again.
Hello.
From when you speak to the customer about what they need and to actually following through and making the thing, what's the time between that? How long does that usually take?
That's a great question. Yeah, it's really fun to actually, like, I design stuff or whatever, design a coating, custom lenses or whatever. It really just depends. Sometimes you can get like a flat optic that you're going to use to make like a mirror or a filter or something like that. You can get those fairly quick if you need a custom one. Sometimes, but yeah, usual manufacturing time for optics is between like 3 to 6 weeks. 3 being like the shorter end. 6 weeks is very typical. If you're dealing with something like a non-spherical lens, like an aspheric lens or something like that, higher end optics, they take longer time, 10 weeks. And then coating, we're always busy with our coating, so that adds additional time. So, you know, it could anywhere, typical 6 weeks. But yeah, it could go up anywhere like 10 to 12 weeks as well. Yeah, it's fun to like, in addition to the coatings, I design custom tooling that holds custom substrates. So a lot of what we do is custom. The standard tooling we have doesn't allow for certain sizes. You can only get maybe 4 pieces in one run. So when I design a custom tooling, I can get 12 pieces in there. And so it's fun to design it in my 3D CAD model, bring it to life, and then throw the custom substrates on there. I don't know, it's cool.
What's the 3D CAD software that you use?
We use Inventor, but obviously many college students are familiar with SolidWorks. But I think they're very similar, is what people have told me.
So if someone got a little bit of SolidWorks experience and then said in an interview, well, you know, I've done 3D modeling in SolidWorks and I'm sure I could get up to speed on whatever package you're using, that would be a credible statement.
Yeah, I mean, if you could do a little 3D modeling, again, like I said, you know, I think most places, unless you're saying specifically that you're very experienced with something, they're going to know that you have like a base level knowledge of something. Unless you're saying I have more experience than that. So yeah, if you guys could get a little SolidWorks and that's not a big deal for you, like that's another thing that's super useful in, at least in the optics industry, but in other industries as well.
We have time for 1 or 2 more questions. Do any other students want to ask something?
I just have one question.
Sure.
Back on the ion beam sputtering slide, you said that the lasers I just wanted to know, like, why do the faster pulses of the laser, or like how does that really affect ion beam sputtering and why it's important?
I guess I should clarify. So what I was saying about that is ion beam sputtering is kind of the preferred coating technology that's used for these ultra fast lasers that are in the femtosecond regime. So 10 to the minus 15 seconds pulses. And the reason why is because the films are so dense and they're so compact and everything that they basically are non-absorbing. And that's like a super important factor when you're working with ultra fast pulses and just high power optics, high power lasers, I guess I should say. So it was really more of a kind of saying that it's like a little bit of a higher end technology. And so it's not necessarily required for ultra fast, but it's definitely the preferred coating technology for people who work with those kind of lasers.
Okay.
Oh yeah, one other thing I want to just say is, there's a lot of different like optics companies. Like I said, my company is like more Japanese based, but I have a friend and he works for a laser company. And he got to go to Switzerland for 2 or 3 weeks.
Sweden, you mean?
Sweet, thank you.
You're talking about
sorry.
Jet.
Yeah, I'm talking about Jet. Yeah, he got to go to Sweden for 2 or 3 weeks. So, and I've heard similar experiences. My friend Kate who was another Cal Poly physics grad, she got to go to Germany. So, a lot of these companies is cool. If they're not U.S. based, then hopefully they'll get to send you to wherever their manufacturing is done. And so, yeah.
Kate who?
Kate, she had long blonde hair. I forget what her last name is.
Caitlin.
Yeah, Helmuth.
Caitlin Helmuth. Okay, yeah. She works at Trioptics. Yeah, they're in Germany. Yeah. That seems to be a nice rite of passage for new grads working for foreign corporations, that you get to have this sort of study abroad. I'm guessing that when you went to Japan, you also got to have a certain amount of fun, a certain amount of cultural exposure, see some trips on weekends and stuff.
Yeah, the weekends I had to myself, and it was definitely an interesting experience being in another country where the predominant English language is not English or anything close to English. And I luckily I had met some of these people who worked at the factory at a trade show that we do every year in San Francisco. And some of the people from the factory come out to the trade show. So when we were at the trade show, I thought they were just the funnest people, and we were just hanging out. And after the trade show, we go out to dinner and we have some drinks and stuff like that. And so you get to just socialize with people within your company. And so thankfully, I knew some of these people when I went, so they were so kind enough to like show me around and take me around Tokyo. So yeah, it was a really amazing experience. I wish I had a little bit more time to myself because I was literally working like factory hours every day, which is like 8 a.m. to 6 p.m. So the weeks were definitely work. And so it was really nice to have the weekends to myself.
All right, well, we're at the end of the class session. So thank you so much for doing this. And I hope that next year we're able to have you in person for an alumni panel.
Oh, that would be great.
Yeah, I think we'll be fully in person next spring. So
awesome.
Thank you again. Have a good evening, and everyone will continue next Tuesday talking about multiphoton microscopy. And I'll keep this open for a few minutes if anyone has additional questions for Kyle. Otherwise, have a good weekend.
Dr. Small?
Yeah.
I just had one question about the previous project, actually.
Okay.
On project 12, on the feedback, it says that you didn't see any graphs for part 3.
Okay. If I missed the file, then I will happily correct that.
I just wanted to confirm. Let me just look at it real quick.
Well, we probably shouldn't be recording a grade discussion, so let me
Oh, okay.
stop